Hello to this video that is discussing the Prince model for determining what the maximum efficiency of a solar cell is. We looked in a previous video at the Trivich-Flinn model. So in the Trivich-Flinn efficiency model, the idea is that each photon has a certain photon energy HF, and we can only extract the bandgap energy EG to the external circuit. So for a semiconductor solar cell, we have an electron moving in one direction, we have a hole moving in the other direction, and then we can extract, following the Trivich-Flinn model, the maximum energy of the solar cell that is given by considering absorption and thermalization. Now, already in 1955, this was extended here in order to consider what is happening in the external circuit, because the Trivich-Flinn model doesn't even have any load here. It just considers the solar cell itself. But in reality, we always do have a load, and I'm showing you here again the schematic with the load on the solar cell. The load is here just this resistor called R consumer. So if we have a load on the solar cell, then it means we have here a certain current that is at the maximum power point and a certain voltage that is the maximum power point. So in the external circuit, we need to consider that the semiconductor solar cell is connected to an external circuit, and consider the overall efficiency then of the power that reaches the circuit, the load, where we want to use the electricity. And this consideration that the solar cell is not just standalone but is connected to a circuit was in 1955 investigated by Prince, and he published actually two different kinds of models for the solar cell. And in this video, we are going to look at the first model, which is a simple diode model for the solar cell. And then if you have the model for the solar cell, we can connect it to the consumer and see what is the maximum efficiency we can get if the semiconductor solar cell follows the IV curve of the simple diode. So let's look at the simple diode equivalent circuit for a solar cell. And this is it here. So the solar cell is a semiconductor device that typically has a P and an N-doped region, and you will learn more on that in a different video. So we can model it by a diode, and also we have the photons that are generating electrons, and these electrons are then given as this constant current source here, where pH, I photon, is the photocurrent that is generated by the solar cell. So we have the diode in parallel to this constant current source that is sourced by the photons. So we have an electron current that is following an electron flux that is following the photon flux. And this is then called the photocurrent here. And if we are setting up the equation for this, then we have here the equation that the total current I that is available externally, the total current I, is this photocurrent I pH minus the current through this diode here. And therefore we get the equation for, if we plug in the standard model for a diode is given by IS, which is the reverse bias saturation current, multiplied by this exponential -1. So the exponential has the voltage U, so the applied voltage here to the diode, and is divided by N, the so-called ideality factor that is somewhere between 1 and 2. The voltage is divided by UT, which is the temperature voltage, and this is calculated by the Boltzmann constant K times the temperature, the absolute temperature, divided by the elementary charge Q. And the elementary charge is given here. Also, I've given here the Boltzmann constant that need to be plugged into this equation. So if we calculate this for room temperature, which is an absolute temperature of 300 Kelvin, we obtain that the temperature voltage is about 25.9 millivolt. So this is the value that needs to be plugged into the equation here. So this is the simple diode model. So now let's look in MATLAB what actually the IV curves look like for such a simple diode. IV curves, the current voltage curves or characteristics, look like for the solar cell. And we are starting with doing here in the script some definitions just in order to make the script more readable. So I define that, for example, nanoampere is 1 times 10 to the minus 9 and picoampere is 1 times 10 to the minus 12. This is just in order to later on be able to write that the reverse bias saturation current is 1 picoampere. It doesn't have any other meaning, just to make it more readable. Okay, so after these definitions, then I define here my variables and I say I want to plot the, first of all, I'm just looking at a simple diode without any photocurrent. So for the diode, I say I want to plot the diode characteristic from -1 volt to 1.2 volts. I set the ideality factor N to 1.5, the temperature voltage to 25.9 millivolt, which I had also defined up here. The reverse bias saturation current I put here as 1 picoamp, and this depends a lot on the material. This is a material characteristic, and actually back to when Prince was doing his paper in 1955, this was a lot higher still than it is in good devices today. So today something like 1 picoamp is realistic. And then our diode equation is given here in the MATLAB code. So we have the saturation current multiplied by the exponential function of the diode voltage divided by ideality factor times the temperature voltage and -1. Okay, so then I plot this graph here, and this is the standard diode IV characteristic that you can expect. So you have probably seen this before in other courses. I'm showing here the voltage again as U, as is typical in Germany. So it's U in volt and the current I in amps. And you can see here that for negative voltages, this is very close to 0. Actually, if we have higher negative voltages, this will go to the reverse bias saturation current of 1 picoamp that we defined up here. At 0 voltage, if we plug in 0 for UD, this exponential function, exponent of 0 is exactly 1, so -1 is 0. So at 0 volts, we also have 0 ampere. And then we see that for positive voltages, we get this exponential characteristic here that is typical for a diode. So this is the diode curve we get for the parameters that are defined in the script up here. Okay, so this is what a diode looks like. And then in order to go from the diode to the solar cell, we need to add the photocurrent to this diode current here, as we just saw on the slides. And this I do then in the next step. And I actually defined again here the different parameters, so I can easily change this block here and plot newly. And what I do now is I define a photon current, photo of 1.5 well, let's start with 1 amp of, let's say we plot one for 1 amp first. So I define it, the photocurrent, as 1 amp. And then again, I plot now the total current I, that is the photocurrent minus the diode current. So let's run this section. And now we get the graphic here, and that is what the graphic looks like. First of all, we see that we start out here at a positive value, a bit higher than 0, and that we go to very high negative values. And this is, of course, because we take minus this diode characteristic, and this diode characteristic is going to 25 amps here if we go, if we are not limiting it, and we are going somewhere above 1 volt. So if we do minus this, then it goes to a very highly negative value. Now, if we want to operate the solar cell as for generating electricity, this part down here is not interesting, because in this region where we have a negative current and a positive voltage, it would just mean that that we have a consumer and not a source here. So what is really interesting for us is actually this area up here where the current is positive and the voltage is positive. So let's just zoom in a bit more on that. Rerun the section, and I just put that I only want to see the positive part. And now we see here only the positive part of the curve. And this is the part here where we have positive voltages, so this area, and a positive current. That is where the solar cell is generating electricity. And so we can see what in the simple model, one diode model, we have in terms of a solar cell IV curve. And we can also check what happens if we use other photocurrents. So let's just use a photocurrent here instead of 1 ampere. Let's do 1.5 ampere, and I just change the color here so it's not looking exactly the same. And I have to take out that it's not clearing the figure. So let's plot this. Okay, so now we see if we have 1.5 amps, we have a higher photocurrent than at 1 amp, and the whole IV curve is moved up here. And if we go down, let's just go to 0.5 amps here and do it in red. Let's plot this also. So now if we are at if we have 0.5 amps of photocurrent, this is moving down. And so what you can see here, if we have less photons incident, it means we have less current, photocurrent. If we have more photons incident, we have more photocurrent. So depending on the illumination condition, we will have a different IV curve. So the IV curve is not a constant for a solar cell, but the IV curve depends on the illumination condition. So for different illumination conditions, we have different IV curves that are mainly shifted up and down, but they can actually also change in shape, because this is a very simplified, the very easiest model. And so in this model, it is only shifted up and down. But in reality, we see more effects. Okay, so we have now we can now plot these different IV characteristics for our solar cell. Okay, so we just looked at the different IV curves for a simplified solar cell model where we just assume the solar cell as a diode with a constant current source in parallel. And of course, what we want to know is how much power can be extracted, or what energy can be extracted from the solar cell. So what we need to do is we need to calculate the power at different operation points. And in order to do that, I just copied over the plotting of the solar cell spectrum to this script here. And now I added here a calculation of the power in this graph. And the power of the solar cell is obtained by multiplying the voltage at the point of operation. So for example, the voltage here of at 0.2 with the current at this location. So if we are at 0.2 volts, we have to take this current here of approximately 1 amp in order to calculate the power in watt. And this can be done for each of these points here. And that's actually what I did, and obtain this curve here. So if we have 0 volts and 1 amp current, then 0 times 1 is 0. So at 0 volts, we have 0 power. If we are at this point here, where the current is 0, then we can multiply the voltage of 0.8 volts with 0 amps, and that is also 0. So at this point, we have 0 power. And at this point, we also have 0 power. And in between, we have a positive power if we are operating in this quadrant, the solar cell. And that is what is shown here. So for example, at 0.2, we have 0.2 volts times 1 amp is 0.2 watts. And for all of these different values, we can then calculate what the power is. And we actually see there is one value where we are at the maximum power. And this is called the maximum power point. And here the maximum power point is at something like 0.65 watt. That is the maximum power that can be extracted out of the solar cell if the solar cell has the IV curves with 1 amp photocurrent as shown here. And I just show you quickly how I actually calculate the maximum power point and plot this. In order to calculate the maximum power point, I do a minimization actually in MATLAB. So this depends on the program you use, what you do, but in MATLAB you can use the function fmin_search, which finds a minimum of a function. And since it only finds minima of functions and I want to find the maximum here, I need to invert it. So I need to put a minus sign in front of the power. So I define this function MPP here for calculating the maximum power point that is has as a variable the voltage U, and then I just put it as minus U times the current that we have defined already up here. So the current is given by I photon, the photocurrent minus the diode current, and this is what is multiplied with the minus U, and then minus U times I is the negative of the power, and this function I want to minimize because then U times I is maximized on the other hand. And so for this I use the fmin_search in MATLAB, put in what the function name is, put in an initial guess. So I say initial guess at 0.5 volts is the maximum power point, and then it does here the then MATLAB does the search for the minimum and puts then the minimum value for the voltage in this U maximum power point, or not the minimum point, the minimum of the inverted power value. That corresponding voltage is put into U maximum power point, and then we can calculate the current I just by dividing the power, the negative power, by the voltage and also adding this minus sign here. And of course the power at the maximum power point also is the inverse of this negative power here. And we see that the maximum power that is obtained is 0.6544 watts, so approximately what we also saw in this graph here. And then I plot in the graph the values that I calculated for I times U, and this is the blue curve, and I calculate the maximum power point. So this is one algorithm of how you can do such a plot of how the power varies with voltage and how you can find the maximum power point for the given IV characteristic. Okay, so we just calculated in MATLAB for this simple model here what the IV curve is, and this is again given here for 1 amp of photocurrent. And we have seen that we can calculate for the values of 0 volts to this crossing point here to the negative values. This is called the open circuit voltage. We can calculate all of the power values and then define where the maximum power point is. And therefore, we now know what power we can extract for a given IV curve. And Prince actually in 1955 put all of this together, and he then said, okay, you have to assume that you have some IV curve and you cannot extract all of the power as was suggested by Trivich and Flinn in this eta Trivich and Flinn, but you also have to consider the current voltage characteristics. So Prince said, okay, you have to take the short circuit current, that is the photocurrent, that is just given by the elementary charge times the photon flux times the area. And you need to consider the open circuit voltage, that is the same as the band gap energy divided by the elementary charge, as the in the best case scenario. So if you multiply these two, then you get the extracted power that Trivich and Flinn suggested as the maximum power that can be extracted. But in reality, you cannot run the solar cell at the point of the short circuit current, which is here at 0 voltage, and the open circuit voltage, which is here at 0 current. Because as we saw before, I mean, not both conditions are simultaneously possible. The device cannot be run at the same time at short circuit and open circuit, but it needs to be run somewhere in between, as we saw up here. And this maximum power point, Trivich and Flinn then said, okay, the maximum power we can extract is given by this voltage at the maximum power point multiplied by the current at the maximum power point. And then he defined this ratio of what he said is the maximum power that can be extracted and the Trivich and Flinn maximum power, which is U open circuit times I short circuit, and called this the fill factor. So the fill factor is the ratio of this kind of like correction factor to the Trivich and Flinn model, what needs to be considered, that needs to be considered in addition to the effects considered by Trivich and Flinn. And so the efficiency following Prince is the Trivich and Flinn eta multiplied by the fill factor. And looking at that graphically, the fill factor basically is the question of how much of the area under the curve can be filled, so to say, at the maximum power point. So if you have the characteristic IV curve as given here in dark blue, then first of all, the Trivich and Flinn power would be the cyan-colored square here. That is the square of U open circuit multiplied by I short circuit. And that gives you this complete cyan-colored area here. And the power that can be extracted then, considering the electrical characteristics, is this blue square, which is given by the current at the maximum power point multiplied by the voltage at the maximum power point. And so the fill factor that we have defined previously is actually the ratio of these two shaded squares here, or rectangles here. So that means if you have a fill factor of 1, then that would mean you would need to have a solar cell with a characteristic that is an ideal edge kind of. But that obviously you won't have for a real solar cell, but you have some IV curves with some bending. And therefore you have this loss that is due to the electrical characteristics of the solar cell. So in order to summarize this, what the Prince model does, it takes the Trivich and Flinn model that is given down here again, which considers which photons are absorbed and how much energy do we lose to thermalization. Additionally, it takes this fill factor effect here into account of the electrical circuit, that you cannot run a solar cell at the same time at a short circuit current and open circuit voltage, but that the real maximum power point is always somewhere in between. And therefore, then the Prince model is in total multiplying the fill factor times the efficiency of the Trivich and Flinn efficiency model. And so here, for the case I've shown here, I actually calculated that the fill factor is 81%. So that means that Prince predicts that the maximum efficiency of power conversion for the AM 1.5 global spectrum, I calculated it here, for a band gap of 1 electron volt would therefore be 39%. Multiplying the 48% by Trivich and Flinn with the 81% due to the fill factor effects. And now you already see that not all of the solar energy that is reaching the Earth can be used in a semiconductor solar cell for generating electricity. But already just these three effects we considered so far mean that you can only use 39%. And you are already down in efficiency now to 39% of the solar energy that you got onto Earth can be converted to electricity if only these effects happen. Thanks for watching.